To Einstein and back.
I like the back. So I don't know, for those of you who saw the title, you know, the original title was actually I don't remember what it was, From Delegation to Einstein, or Where Delegation Meets Einstein. But you know, with Buzz's advice, actually, since we're here in the Newton Institute, you know, it's not nice just to mention, you know, Einstein and not Newton. So, okay, so we're going to go from Newton to Einstein. Okay, so let's start with the problem of delegation. So what is the problem of delegating computation? So there's a verifier here who wants to compute some function f, but he's very weak. He can't do it on his own, and therefore he wants the help of a prover to help him prove. He wants the prover to help him do the computation. So he is kind of a worker for him. He'll help him do the computation. He computes the function for him. He tells him f of x equals b. But the verifier does not necessarily trust him and wants to prove that indeed f of x equals b. And so, you know, they may talk back and forth, and now, you know, hopefully the verifier is convinced of the computation, that the computation was done correctly. And we want to ensure that a cheating prover cannot convince him of a false statement. Okay, so that's the power of delegation. You want to delegate a computation. You want to prove that the computation was done correctly. So this is very, very similar, you know, to interactive proofs, a notion that was defined in the mid-'80s by Goldwasser, Mikhaili, and Rakov. So in what sense is it different? It's actually exactly the same. The focus is just different. So here, often when we think about delegation, and it may be convenient to think about it throughout this talk, is we think actually of the function as being in P, perhaps. Okay, so it's not very, very difficult functions. It's functions that we may want to compute day to day, but this verifier may be very, very weak. For example, he may be you know, a cell phone. So he's supposed to be very, very efficient. Okay, you may think of him as he can run in time that depends only on the input, but his running time should not depend on the function being computed. So the function can run in time, the input of the size n, the function can run in time, you know, n to the 5th or n to the 100. Okay, and his running time should be independent of the runtime of the function. Okay? So this is so we want a delegation scheme. Okay, so we want such a scheme. And the focus of this talk is on trying to get two-message delegation schemes. And we will assume, as opposed to interactive proofs, which usually, actually this is joint work with Ron Raz and Ron Rothblum. They were on the first slide, but I didn't mention that. So we will think of the other difference from interactive proof is that these are arguments. Okay, we're focused on arguments. So the prover, we don't offer soundness against any all-powerful cheating provers, only against computationally bounded cheating provers. Okay, so can we do it? You know, do we know how to do delegation? And here is what's known. Okay. We know how to do, if you look at the scaled down version of P, you know, all you care about is the functions in P. We know how to do it for log space machines, okay, or more generally from uniform NC circuits, okay, under computational assumptions. But the really, really interesting problem is can we do it for P? Can we delegate all functions in P? And this is not known, okay? So let me tell you, there's been a lot of work on this, on delegation. And let me mention some of them. So first, as you noticed, I'm focusing on P and not on NP. And one of the reasons is because these guys, Gentry and Witch, who showed that actually for NP, you can't do it under falsifiable assumptions. Okay, and we want to do falsifiable assumptions, so you know there's no hope to do NP. We'll try to do P. And actually, when you think about the context of delegating computation, often you know, when think about, you know, the cloud, when you want to ask some cloud to do some computation for you and give you a proof, then usually it's P that we're actually interested in this setting. So we want to do P. There have been, yes?
That says nothing about delegating for P, the negative result.
It says nothing for delegation for P, no. Right?
Yeah.
Okay. Then there's been a bunch of interactive solution, interactive meaning more than the two message, so 4 message or more, okay? Some of them are arguments. We know how to do four-message argument systems, and we know how to do there's been work on interactive proofs, delegation, which is many rounds, but proofs as opposed to arguments. And then there's been a lot of, there's been some work on so our goal is to get non-interactive. When I say non-interactive, I actually mean two-message. Okay, so I'm not really non-interactive, but just back and forth. So there's been attempts to try to get these interactive proofs and make them non-interactive by somehow reducing this interaction. And there's two main approaches to do that. The very well-known Fiat-Shamir heuristic is one way, and that's what Mikhaili proposed. And another is what I will call the peer heuristic, which was proposed by Aiello et al. A very beautiful way, and I'm going to focus on that. I'm going to talk more about that in the next slides. And then there's been quite a bit of work on the pre-processing model, which says essentially in some offline phase, the verifier is going to do a lot of work, okay, but then during the online phase, he will work very little. Okay, so there's been a lot of work with various parameters and so on in this model, which I don't want to get into. And finally, there were also some works that did delegation non-interactive, so two-message, but under non-falsifiable assumptions, and these were for NP. So these kind of match the lower bound of Craig and Daniel. Okay, so that's some kind of a very, very brief overview of previous work. And now let me tell you what our results here are. So we show a strong connection between two-message delegation and no signaling or multi-prover interactive proof, which I'm going to abbreviate by MIP, that are secure against no signaling provers. So just so I have an idea, does anybody know what no signaling provers are? A little bit like, okay, good. So you learned something. Okay. So we show a connection. Okay, I didn't know what no signaling provers were either before I started working on this. So before I go into what no signaling provers are, let me just remind you what MIP is, what a multi-prover interactive proof is. So it's a very beautiful concept that was put forth by Benno, Goldwasser, Kilian, and Wigderson in '88. And essentially it generalizes the interactive proof concept, where now there are many provers, okay, and the verifier, so if the verifier wants, proof of that X is in some language, what it does, he sends some query to these provers, he gets back answers, and based on these answers, they're supposed to convince him. He's convinced or not whether, X is indeed an L or not, so that's a proof for him. And the soundness holds with respect to any adversaries, so cheating provers, as long as they do not talk. Okay, so as long as do not talk, as long as you know that these provers do not talk after they get the queries, then you know that you're convinced of the soundness. So they can't cheat. They can't convince you of an incorrect statement. And what's really nice about this model, as was shown by Babai and friends, is that as opposed to the IP, which we know is equal to p-space, this has much more power. What you can do in MIP is you can prove all of an exp. Okay? And by the way, let me just mention, in this work, during this talk, I'm sometimes going to focus on P, sometimes going to go to exp. Everything I say scales up or scales down. Okay, so whatever I say about P scales up to exp. Whatever I say about exp scales down to P, and I'll mention that as I go along. And please feel free to interrupt me with any questions. So are there questions? Okay. Okay, so there's these MIP, okay? We know how you can do next with MIP. And then there was a very beautiful paper by Aiello and friends who said, okay, here's a way to construct one round or two message arguments, okay? And actually, I think they did it for PCPs, not for MIP, but it's essentially the same. So I'm gonna quote them for MIP, but I think what they did is actually for PCP. So here is their idea. What they said, okay, there's that, how do I get delegation? You know what? I'm gonna send, just as the prover, the verifier, to send all the queries ahead of time to the same prover. Obviously, this is not secure, okay? But their idea was, don't send it in the clear, but send each one kind of encrypted. Okay, and what they proposed is to use a peer scheme, a private information retrieval scheme, a computational peer scheme. I'm actually, for this talk, I'm going to always use fully homomorphic encryption. They didn't know that they existed, but actually they make all the notations much easier. So thanks to Craig, I have an easy job of using the FHE notations, but you can do everything with peer. You don't have to resort to fully homomorphic encryption here. But their idea was but the verifier will just send each query. He'll send all the queries to the verifier, but each query he won't send it in the clear. He'll encrypt it using a fresh key. So he chooses, I didn't write here all the keys because it will be too much notation, but essentially he chooses public key 1 and encrypts Q1 under public key 1. He chooses public key 2, encrypts Q2 under public key 2, and so on and so forth. He sends all the public keys and all the ciphertext. So the prover gets all the queries encrypted. And what he's supposed to do, he should send all the answers encrypted. So he computes each answer under the FHE, underneath the fully homomorphic encryption. Okay? Any question about the scheme? Is the scheme clear? Is their suggestion clear? So this is, I think, very natural and very, very elegant way to get two-message arguments. And their intuition, or our intuition for why this may be secure, is to say, well, when he needs to answer, when he needs to give one answer, okay, he sees these encryptions, the other encryption, but it's a ciphertext. It's it gives no information, so soundness should still hold. So that's kind of an intuition. However, shortly after this notion, or not so shortly, I don't know, after this notion was proposed, even before. Came a very beautiful. Shortly before. Came a very beautiful paper of a Dwork and then the friends. It's there are too many authors to name. But what they showed, which was very nice, is that this is actually not secure. And first, they gave an example for an actual PCP which breaks the soundness, and moreover, they showed that this PCP can be, there's also an MIP, for which the soundness breaks. But more than just giving a counter example, it was, at least it was very convincing in the sense that after you read the arguments, you felt like it's not just an esoteric example. You were pretty convinced that that this should not be secure.
Yeah, I mean, if you just use FHE, it's obviously insecure, right? If you use one FHE, for example.
Oh, one, yes, but it's
right,
public keys, different public keys.
Right.
Then it's not clearly insecure.
Well, if you use the not thing, I guess maybe, but yeah.
No, these are independent.
Independent keys. It's very important. Independent keys. If it's independent keys, it's not clear that it's not secure. Okay. And what I'm going to claim is actually in many cases it is secure. Okay. So it's important. Of course, if you use the same key for all of them, then it's clearly insecure. Okay. Because when he's inside the FHE, he essentially knows all the queries. So it's very important. The suggestion was with independent keys. Each one is encrypted with an independent key. Okay. So this was shown to be insecure. It was kind of a bummer, but that's life. Okay, so what do we do in this work? What we show is that if this MIP is secure not just against any prover, but also secure with respect to no signaling provers, okay, and I'm going to define what it is soon, then it actually is secure. Okay, so no matter what FHE uses, as long as it's sounds secure enough, it works. Okay, and moreover, we show that it's pretty tight. So in other words, if you succeed in proving that this is secure using standard techniques, I'm going to get to what I mean by standard techniques later on, then it has to be sound against statistically no cheating provers. Because if there is a no signaling prover that cheats, you won't be able to prove security using standard techniques. Okay, so this is kind of if and only if.
Yeah.
Yes?
There are no MIPs of that form?
There are. I'm going to get to that. You're asking if there's no MIP. We don't know of MIP for P of that form. But I'm going to get to that. Yes, I'm going to explain.
So this Arabic, I'm not trying to understand it. So you're saying if there is a protocol which is secure for every FHE.
Yes. And so if you start with an MIP.
There is a function, something.
Okay, so here, let me say the other direction.
No, this is not secure.
No.
Right, we know it's not secure for general, this translation doesn't work if you don't restrict the MIP.
Exactly.
Okay, so what is this?
Okay, so let me say again the back arrow, okay? Let me explain that again. What this back arrow says, if you tell me that there exists an MIP, you give me an MIP, and you give me a proof that this is secure, and the proof is very standard, I mean using kind of standard black box techniques, then I can prove to you that it must be that this is secure against no signaling provers. So if this was not secure against no signaling provers, there's no way you can prove security using standard techniques. Okay?
And
I'm not
it's true for any FHE, right? It doesn't matter what FHE. If it is secure for some FHE.
No. Okay. Maybe I'll say again. If this is secure, okay. If you prove that this is secure for every FHE, then using standard techniques, then it must imply that top. Now you're saying, but what if it's secure for only one FHE? Then does it imply? So I'll tell you what you need. You need the FHE to be re-ran. This is kind of a side remark. If it's re-randomizable, then it's fine. So that's for the FHE, yeah. Okay. So that's our results. Yes?
So you need this to be a real FHE in the sense compact set.
Compact. Yeah, well, see, if it's not compact, it's not delegation. Okay, so maybe I'll say, when I put here FHE, I'm always thinking about an FHE that's compact. So though I'm not thinking about these very, very long, otherwise this will not be, this will still work, but this will not be good
It won't be
delegation.
private information retrieval protocol.
It won't be a private information retrieval, yes. Any more questions? Okay. So let me just say that after the notion of the Aiello et al. Came out, actually after the Dwork et al. Work came out, for me it was a bit frustrating that it doesn't work. And Ran and I tried to understand it better. What we showed is, okay, if you start with a PCP or an MIP and you try to reduce interaction, it's not sound. We got that. But then we realized, what if you start with interactive proof? And you try to reduce interaction using this peer heuristic or FH heuristic, I guess. And let me say it in the context of when you reduce interaction in interactive proof, you need to be a little careful.
So this whole talk about delegation also talks about the work of the verifier and so forth. We're ignoring all this. We're only focusing on reducing interaction. Is that right?
Well, the work of the verifier, okay, so the work of the verifier is very, very important, okay? So the work of the verifier here is the same amount of work that he works in the MIP.
But in the MIP work, we never really required him to be super efficient.
Okay, so
Actually, we wanted to be super efficient.
yeah, but it is actually super efficient.
Yes, so decrypt, so that's proportional to security parameter. Then he has to do some work.
But it doesn't, okay, so when you do an MIP, think about the exp, I guess. Okay, so when you think about MIP for exp, the verifier is efficient.
You're saying specifically it is true for the MIP equal to X, that it's all logarithmic and that's what you want.
Exactly.
And
It's
language membership count, okay.
yeah, but I want to say if you reduce it to P, it will also hold. Yes. Okay. Any other questions? Okay. So as I said, Ran and I used the peer heuristic to actually reduce interaction in interactive proofs. Let me just briefly explain how you reduce interaction, because it's not very, very obvious. To reduce interaction from interactive proof, the idea is, well, so what do I encrypt? So in one place I encrypt the first query. It reduces interaction from interactive proofs that are public coin. Okay, so take a public coin interactive proof, where the verifier sends public coins, just random strings, and I'm going to show you. And so how did we reduce interaction? The idea was, well, send the first randomness encrypted, then send the two, the two messages of the verifier encrypted under another key. And if there are three messages, then send the three first messages encrypted and so on and so forth. And the prover will just reply with his answer again, exactly as before, inside the PCP. And I just want to focus to say the reason we needed to put both R1 and R2 is because the prover needs to know both R1 and R2 in order to answer the message. If you give him only R2, he won't know, okay? Because his message depends on all the history. So he needs to know this information. And we showed that indeed in this setting it's sound, okay? And the proof was not very, it was kind of messy. There was a lot of mess going on, and Okay, but it worked. But what's interesting is that our result here simplifies tremendously this work, but moreover, I think more importantly than simplifying, finally we understand that work. Okay? The reason it works, and why we can say the protocol is, why now the proof is so simple, the proof is simple because we finally understand. And what we understand is the following. When you look at this interactive proof and think of it, instead of interactive proof, think of it as an MIP, a multi-proof interactive proof, where how do you think of it as an MIP? Think of the first prover getting R1. So the verifier gives the first prover R1, gives the second prover R1 and R2, the third prover R1, R2, R3, and so on. And they each, prover I answers, with the answer I, with the message I of the prover. Then it turns out that it is no signaling. It is secure against no signaling provers.
What is
We
this?
don't know what must.
I know.
But it's secure against even provers that completely collaborate
No.
in any way,
No, because then they see everything together.
you can't learn from the future, right?
Exactly. They can't talk, but it's okay if there are no signaling. So I'm very happy with the question. What are these no signaling provers? Okay. So now I'll explain. So, actually, the notion of no signaling prover is inspired by the community that work on quantum computation. For those who know me, I'm probably very surprised because I know nothing about quantum computation. But fortunately, what?
We know your call.
Yeah, exactly, my co-author. But fortunately, you don't need to know anything about quantum computation to understand this. So, okay, so let me explain a little bit. So apparently, people in the quantum computation community are obsessed with the question of what's the power of MIP with respect to quantum provers. Okay, it's a very interesting question, apparently. Okay, so let me just explain what it is. It's very similar. Okay, so again, there's a bunch of provers. Okay, they get queries, they get answers. You can think of the question consider the problem where the queries and answers are just classical bits, or you can think of the case where they're qubits, so quantum. For this talk, just think of them as classical. Okay, so these are always classical. And as before, this should be secure against, any cheaters. These cheaters, as before, cannot talk. However, they may start with a secret state, exactly like in our case. They can start with a secret state. But here, these secret states, for those who, when they see this notation, they start, to get anxious. This is, these. So they may have a quantum state, okay? Also, by the way, also in the classical setting, we may share a state before we talk, but it's not it's a classical state. Okay, so we may be the cheating prover may be a circuit, and we may share some information before we get the queries. But here they may share quantum information. So in particular, these states can be what's called entangled. After they have these states, though, they're not allowed to talk anymore. Okay, they get queries, they get back answers, and again, for this talk, think of the queries and answers being classical, just bits. And it should be sound against these provers. Okay, so it seems like in this model
the A1 in the quantum state and the A1 in the answer is different, right?
Oh, sorry, I didn't notice that. Yeah, sorry, I'm abusing notation here. The A1 up there and the answers have nothing in common. Thanks, Guy. I'll correct that.
But the queues are all independent, yeah?
Actually, no, they're not. Because in an MIP, often, the way they work is actually, you send one prover one query, the second prover you do some consistency check.
But do you wait, but
No,
for the
they're at the
second
same
prover,
time.
do you wait? They're at the same time as well?
Same time,
Okay.
same
so
time.
yeah.
It's not an interactive thing, okay? The verifier, this verifier sends all of them and then gets all of them back. It's a one-shot thing. Okay, so it seems like this entangled state may give the provers more power. The cheating prover, more power to cheat. Okay? In particular, for example, prover one, what he can do, he can make a measurement, whatever that means. I'm not going to define anything in quantum physics because of ignorance. So he can make a measurement on this state A1, and what will happen as a result, it can cause some collapse in state A2, And this can cause them to somehow not really communicate, but it can cause them to somehow be related to one another in ways that are not allowed in the classical setting. Okay, so this way gives them a lot of power. Okay, and the big question in this regime is, can you do all of next or not? Okay, so in the classical, we know you can do next. With these provers, can you also do all of next? Yes.
It's counterintuitive.
Can you undo for a second?
Yes.
Saying a measurement on A1 will result in some information to the second.
It's not really information, it will cause his state to collapse in some way. And whether this really gives information or not,
This is a detectable event.
no, it's not actually a detectable event really.
But it collapses anyway.
He can't really know if his state collapsed or not.
But there is an example, maybe.
Collapse means that it has been measured.
It has been measured.
But
It has
there is
been
an
measured.
example. There is an example where they can do something with this thing that you can't do.
Yeah, you can do something with it that you can't do otherwise. But actually, I want to say you don't actually need to know what this means because I'm going to tell you what it means in a minute.
There's cheating.
So can you do all of next? You said that this is counterintuitive?
No, I mean,
Oh.
is any of the inclusions here?
Okay, yes, okay. If you insist that the Q's in A are classical, then it's clear that it has no more power than classical MIP, because the protocol is the same and you give the cheaters more power. Okay? If you allow the Q's and A's to be qubits, then it's not clear what's stronger and what's weaker.
Is this known to be stronger than IP?
Probably, yes. I'll tell you, yes. It's known to be, no, sorry. No, it's not known. It's known to be at least, it's known to be at least p-space. But it's not known to be stronger. No. I'll answer you, and I'll get to that in a minute. Okay, so this is the big question. And now you're saying, okay, but what about the no signaling, right? So this is where the no signaling comes in. So to deal with quantum information and collapse and measurement and so on, it's a messy model. So what the quantum people did, actually already in the mid-'80s, what they did say, you know what, let's try to make it mathematically clean model. Okay, and here's how they defined it. So they defined what's called a no signaling prover. A no signaling prover, so you can think of all of these as kind of one prover, okay? And a no signaling prover, they get all the queries ahead of time. They can see all of them, okay? And they can see, and based on that, they can answer. So clearly, if you take the MIP, you give it all, and you let them talk, it's not going to be sound. If you know the MIP protocols, you know it's not sound. Okay. However, there's a requirement, and that there are no signaling. And no signaling means, essentially, that so for example, if you consider the first coordinate, if you fix Q1, if you fix the first query, A1, look at A1, the answer is random variable, it's independent of the rest of the queries. In other words, if you fix the first query, A1 gives no information about Q2 up to QL. Okay, that's what it means to be no signaling. More generally, for every subset of L, if you fix the Q's in this subset, and you look at the answers corresponding to this subset, they give no information on the rest of the queries.
So I don't see your picture. All the QIs go to everybody? No.
You can think of them as just colluding to one prover. Okay, so you can think of.
Why did you draw so many provers?
I put them together because there are many of them, but they can talk and they can.
So
They can't talk.
can I think
No,
of it this
okay.
way? Can I think of it this way? That there's one prover, but he has a strategy that has these restrictions.
Yes, you can think of him as one prover that has
And
exactly.
his restriction is that he works on each slice individually, in the sense.
In this sense, exactly. You can think of him as one prover. Maybe that's a better way to draw it. You can think of him as one prover, okay? Because they're total now. You think of him as one prover. He gets all the queries. He can do whatever he wants, but he needs to be no signaling, which means that the answers for each subset, the answers depend as a random variable depend only on the. So if you fix the queries, it is totally independent of the rest of the queries. So the answers of every subset, conditioned on its queries, give no information about the rest of the queries. And actually, this notion, which Moni may recognize it's very similar to this was essentially, a very similar notion was defined in the work of Dwork et al., where they gave the negative result, and they called this a projection property. So they didn't give really they didn't give a rigorous argument showing a negative result, but they noticed that this is an important, that this is kind of an issue there. Okay. So why am I showing this no signaling? Because it turns out that if you have a protocol like this that is secure against no signaling provers, it's also secure against quantum provers. And yes?
Quantum MIP is in no signal.
No, it's this way. I'll tell you why. So if you have a protocol that's secure, if you have an MIP protocol that's secure against any no signaling, it's also secure against any quantum, and therefore you can do it in quantum MIP as well.
But the completeness thing, like, how is the completeness?
So okay, good. So think of when I say quantum, for this talk, think of the protocol itself. Everything is classical. It's only the cheaters that are quantum. Okay.
So they don't talk. Like in the completeness case,
exactly. The completeness is
classical
MIP.
provers.
Exactly. Think of the completeness as MIP. Everything's the same as MIP. Only the bad guys, all of a sudden, we give them quantum power. Okay, so why is no, and this is where Einstein comes. So why is no signaling contained in quantum MIP? Because actually this follows from the special relativity theory, from Einstein's special relativity theory. So why? We know that information cannot travel faster than the speed of light. So now what you can do, put one prover, in Mars, the other prover in Jupiter, and if they're quantum people and they could be no signaling, what you can do, you can have one verifier here, one verifier there. They'll send a query, get a response, and based on that, he will know what the other verifier, on Mars sent. And look at that speed, information travels so fast. So as long as you don't let them talk, if you put some bound on the time they respond, it turns out that no signaling is contained in quantum MIP, and therefore, people that work in this area often, they just consider the no signaling a MIP question. Okay, it won't, if they get that no signaling MIP, is very powerful, is
Weak.
It's very weak. It won't say that quantum MIP is very weak, but that's one way to go about learning about it. And as you see, it's a clean mathematical model. There's no measurement and collapsing and so on and so forth. Okay. So now we can ask, okay, so what's the power of no signaling MIP? And indeed, there were a bunch of works in this area, and I'm sure this is a very sparse subset of the works that actually appeared. And here's what's known. So they know that if you have only two provers, no signaling is unfortunately a bit weak. You can only do p-space. Exactly, it's a characterization. Okay. If you have many provers, on the other hand, then you have an MIP protocol that's, and the question, what's the power of this? Well, it's contained in p-space, of course, because that you can do with two. And it may be all the way to x, but nobody knows where it lies. Is it in p-space or is it in x?
And you want to project it, right?
I want to project, exactly. Good. Exactly. So what we show, sorry. Yes.
Forget so MIP is equal to x if we don't have it on this non-signal.
Next.
Next, right.
Yes, but in particular x.
Okay, yes.
Yes.
Okay. So you're saying you're weak. You've let your provers communicate to a certain extent. Okay, some restricted extent.
Yeah.
Therefore, they are stronger.
Right.
I don't believe what they say as much, and therefore the set of language I would accept is less. But
Exactly.
they're saying maybe it's up to x, as far as they know.
It may be up to x. We know that it's not more than x. Okay, so in some sense, we know that it's not more than x.
Why is that?
I don't know. Ask them. They proved it.
Not something simple.
Actually, it is something simple. So it follows from a linear programming type, dynamic programming type thing, but I don't know the details.
The other direction, you also claimed it was simple. That
No, I didn't claim it was simple. I claimed it was known. What? Oh, sorry.
That
What?
you said that if you have a truly interactive provers, then they are like non-signaling or something like that, right? Because before you said that U result gives a simpler proof of your
Oh.
previous result you've run.
Okay, what I said, if you start with an interactive proof and you convert an interactive proof to an MIP, oh, you're saying that the fact that you can do p-space
Yes.
is quite simple. Yes,
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 so I
right.
think-
Yeah, okay, that part. Yes, yes, yes. But what's not simple is that two prover is not more than p-space. That's the hard, it's pretty new. I think it's ITO 10, 2010. He proved that you can do more than p-space, and contained in exp is some kind of linear programming. Okay. So how does it? So this is, let's go back. So this is our result, right? So essentially, what we show is the idea to try to do it for NEXP with standard proof techniques won't work. Okay, and that was the intuition we got from the Dwork et al. Paper, but this is kind of formalizes it. But more interesting, I think, is that we show you know, don't worry, for exp it may work. And if you look at the scaled down version of P, we still have hope. Even though we thought that it was hopeless, there is still hope because there may be no signaling protocol that are secure for P, for X. Okay. So, any questions?
So in other words, if you can come up with an MIP protocol,
Yes.
which is and prove that it's
I'll get to the statistical. Let's say no signaling for now.
and prove that it works against no signaling provers
Mm-hmm.
with this fully quantum, with this restriction on the distribution of answers in
Exactly.
then you can just use that transformation with a fully homomorphic encryption scheme, anyone,
Yeah.
and you'd have the two messages.
Yes. 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 Boss.
Do these quantum people have a belief? What is the power of non-signaling
It
provers?
doesn't matter quantum anymore.
I mean, yeah, no, but they work on no
maybe they have
signaling.
intuition. Is the truth? Is it closer to X or closer to
You know,
p-space?
I don't really know. I think Ran may, you know, I feel funny quoting him. Maybe X, but I don't think it's a conjecture. Okay.
What's not a conjecture?
So Boz asked, what's the power of MIP with no signaling provers? So I said, do they have a belief? So I said, I don't think they have a conjecture.
Oh.
You know, I think maybe there may be X, but I'm saying it very, very hesitantly.
So
Yes.
when you scale down, it's log space versus p, right? So,
Yes.
so do we know any examples of things that not one example of a function which we believe is not in log space, but we can do this no signaling? You see what I mean?
Yes.
One example of function that's not in p space, right?
That would give you conjecture that
We don't
it's
know.
not equal to
Because
p-space.
yeah, exactly.
Okay, that we don't know.
Yeah, we don't know.
I see.
We don't know that MIP with no signaling is not p-space.
Even under conjecture.
Unless you conjecture that.
No, but there is no like natural conjecture.
Yeah, we don't have. I mean, you can take a.
There is-
You can take a. If you take a standard MIP, you know the most common MIP. Actually, okay, if you take, I can. There are MIPs for EXP, for which I think they may be secure against no signaling provers. I don't know how to prove it, but I can conjecture it.
What's the size of the subset
Why
you're
not?
talking about?
What's this?
The signaling. I mean, it's all about subsets, right?
All subsets.
Any subset. So there's L provers. L is not big. I mean, L is the number of provers. For any subset of the provers, you need the property that the answers are independent of the rest of the queries.
It's meaningless if it's the full subset.
It's the full subset. It's meaningless. Yes.
Full subset is just MIP. No, I'm misunderstanding.
Well, if it's a full subset, you're essentially saying that take all the answers. They don't give any information on nothing else. So the no signaling
Full subset
essentially
is like
says.
a one-round interactive. So you can answer whatever you want. There's no-
The singleton subsets are like
Okay. The singleton subsets.
Yeah, you can think of singletons if it makes life easier. They do have actually, I think, some results about what's the power for MIP no signaling for singletons. There is some result. I don't remember what it is, but it won't help our setting. So there are various kind of ways that various results in this regime. Yes.
And just to check, so this is about this particular approach, right? So you're saying if you try to take this MIP with like PIR and so on, but it's conceivable that, for example, we can instantiate Fiat Shamir and get an
Exactly.
alternative result of it.
Exactly. I'm not saying that it's if you show that MIP with no signaling is in p space. I'm not claiming that you can't do two message for exp okay? And maybe with other techniques, but not this one. Okay, so let me say a word or two about the proof. So let me, one thing. There's the statistical there that I kind of hid. I hid because it's not very interesting, but I'll just say what it is. So statistically, no signaling just means, well, it's not really independent, it's statistically close to being independent. Let me shove that underneath the table because it's a technical thing, it's not very interesting, and it doesn't really affect the results. Okay. So, let me say a word about the proof, unless there's any more questions.
So whatever it's computational, I don't know if the notion makes sense. If it's computational, non-singling, whatever.
It's not just perfect, it's statistical versus perfect.
Yeah, it's not computational, it's
But
statistical. You're asking about the computational.
Yeah.
It
Does
may,
it make sense?
so it may make sense. It wasn't defined. Statistically, was a notion that was considered. Computational, it wasn't considered. It may make sense. I don't see it. I mean, we have a tight.
It's not
Exactly, we have a
sufficient.
tight reduction, so I don't see computation. But it's
It's not
some.
sufficient for your results. So
Exactly.
for important result, you really need statistical.
I need statistical. Yes. Okay. So this part is actually straightforward. Okay, it's very easy. It's the negative result that requires is the technical part. So let me show you how you do the positive part. Okay, positive part is really easy. Okay, so we started with an MIP that's secure against no signaling, or statistically no signaling, and we want to prove that this is secure. Why? Straightforward. Suppose not. Suppose that there is an adversary that cheats. I'm going to construct an adversary in the MIP setting, but this guy is going to be no signaling. Okay, so think of them according to Shafi's suggestion. Think of them as one. They see all the queries. The one, he gets all the queries, he answers, but he needs to be no signaling. I'm going to give you such a prover, and he's very simple. Here's what he does. Okay, so this is one prover. He's a no signaling prover. Here's what he does. He gets the L queries. He himself encrypts them, sends it to the prover up there, gets the answers encrypted, decrypts, and sends these answers back. Okay, so he just emulates the above prover. So clearly, he breaks the soundness. The above breaks it, so he breaks it too. Wait, what takes a little work, very little though, is to show that he's no signaling, that he's statistically no signaling. Okay, here we need the statistical. And I'll give you the very high-level idea. The very high-level idea is, again, very simple. The idea is the following. Well, otherwise, suppose he was not no signaling. What does it mean? It means that there's some subset for which these answers actually depend on the other queries. So condition, fix a set S, fix queries QS. The answer depends on the other queries. Now what I do, I'm going to use that to break the FHE. How do I use that to break the FHE? What I'm going to do, I'm going to get an encryption of the rest of the queries. Not the QS. QS I know. I'm going to get an encryption of the rest of the queries. I'm going to send it to this P star, get his answer. I'm going to look at my AS. Okay, and then I'm going to see. Okay, it depends on the rest of the queries, and I'm going to gain some information about it. Okay, and that's how and the reason I break it in there's this sub-exponential time that comes with us everywhere. Actually, this is because the distinguisher who distinguishes between AS, given the other queries are of one form or another form, is unbounded, it's statistical. So he may run in time 2 to the size of A. This is a very technical point. Let me just say that you can break it in time, essentially in the time of P star, and exponential in the answer size. So, if you start with an MIP, let's say where the answer size is logarithmic, I'm looking at the scaled down version of P, and you start with, let's say, answer size which is logarithmic, you don't get sound, you only get 1 over poly soundness, but then this is poly. And now so there's some kind of trade-off between soundness and the running time it takes to break the FHE scheme. Okay, but another way is just to think about as a sub-exponential time, and so that's a technical detail. So this direction is straightforward, is relatively simple for people who didn't follow. Don't worry, it's not very interesting. It's kind of the straightforward thing. Okay, so the technically interesting direction is actually the negative result. Okay, so in my opinion, the conceptually interesting direction is the positive. The technically interesting is the negative. So let me say a word or two about the negative result. So what I want to, essentially, in order to prove our negative result, what I'm going to show is that let's say we start Actually, before that, are there any questions?
But just to check, I mean, it's sorry.
Oh, yeah.
No, just to make sure it's a triviality, but some who seems counterintuitive.
Do you want me to go back?
Not the proof, but just the logic of the implication. So you're saying that for the special case of MIP, this technique kind of works, right? So,
Right,
so this technique
exactly.
works. Namely, there exists a counterexample here, there exists a counterexample there, but it's a little bit confusing. Why? What if I remove statistical non-signaling? It seems like there is less to prove.
No, so what
because those guys have the answers together. So
what can happen? Yeah, okay.
Got it. Sorry.
You got it.
I'm slow.
Okay.
Yeah.
Yes.
So how about verifiable computational preprocessing, right? Of course, you get it in the positive result, right? Obviously.
Wait, you're saying, oh,
With
you want to go to the pre-processing
Yeah,
setting?
yeah.
Uh-huh.
Of course, you get it. In the,
Yes.
But the other way around, does it still work? If I mean, the one that you're going to show, does it?
So, okay, let me understand. Vinod's question is, let's say let's say the verifier, we allow him pre-processing time. Do you still get a negative result? So my answer is, I'm showing a negative result for a specific protocol. Let me emphasize, I'm not claiming that there's no two message protocols for X. I'm talking about the specific one. I'm ruling out this one. Okay, so, okay. Okay, so what's the negative result? I'll say 5 minutes about the negative part. So, what I want to say here, I want to say, suppose, let's start with an MIP that's actually not secure against no signaling provers. So there actually may exist, you can cheat if you're no signaling. Now I want to say, it will be hard to prove that this is secure in that case. So we start with an MIP that you can cheat with a no signaling prover, and I'm going to prove that it will be hard to prove security here. So actually, it's not just difficult to prove this result, it's also a bit cumbersome to state this result. So this is obviously a very imprecise statement of the result. Let me spend maybe a few minutes trying to explain this result better. So the theorem, let me first give you the theorem pictorially, okay? So suppose we have a statistically no signaling prover that actually breaks the MIP. I want to prove that you can't use him as a black box. Okay? In other words, what I'm going to say is the following. Suppose, let's say the underlying assumption is that the encryption is secure. For a second, okay? I'm going to say you can't, if you have a reduction or an adversary that uses this prover to break the assumption, let's say, to break the semantic security of the encryption scheme. So he gets a ciphertext. He goes to him with some queries. He gets his help, gets answer, and breaks. Suppose we have that. Then I'm going to show you can do it without the prover. That's kind of the result. And so the way I showed it was a bit specific. So first, I described it with, suppose the underlying assumption is the security of the FHE scheme actually can be from any standard assumption. I'm going to talk more about what I mean about standard assumption in the next slide, but it can be from any assumption, not just the security of the FHE. Also, here I restricted the adversary to call the cheating prover only once. So no, he can call it many times. However, the number of times that I allow my reduction to call my cheating prover should be independent of the security parameter. So the cheating prover essentially, it shouldn't depend on how exactly the encryption works. Think of the encryption as kind of an envelope. Okay, I want to consider the natural reduction. The number of times he calls the cheating prover should not depend on the actual. In a standard proof, it doesn't depend on the actual security parameter. So I'm going to take this, so it should be independent. And if this is the case, then you won't be able to prove. So let me say that now a bit more formally, okay, because it was a bit, okay, so now here's the theorem. So suppose there exists no signaling prover that breaks the MIP. Then we show that you cannot prove, or that the one round argument cannot be proven secure using a black box reduction. Actually, it's according to Mark Fischlein's talk, it's cannot be proven secure using a meta reduction because we rule out actually meta reductions. If first the number of oracle calls that the reduction makes to the cheating prover, is independent security parameter, and B, that the underlying assumption needs to be standard. So if that, you won't be able to prove it using a standard assumption. Now I want to say a word about the standard assumption. I would like to say by now, we'd like to say, oh, we can't prove secure under any falsifiable assumption. However, unfortunately, I can't do that. But it's not our fault. The reason we can't do that is because it's actually the assumption that the scheme is secure is falsifiable. Okay, because a cheating prover, I think we're in the regime of P. Okay, so a cheating prover is actually a proof that the assumption that the scheme is secure is falsifiable. So there's no way I can prove that it's not secure under falsifiable assumption. Because it's a falsifiable assumption and it's secure, so it's secure. So I can't do that. So that's a bit unfortunate. But what we can prove, so now you say, okay, so what's the standard assumption? Oh, yes. Nigel,
Just scratch my head.
Oh, okay. So what's the standard assumption? So there are many ways to define it. We define it in what we thought of as a maybe clean definition, but it probably extends to various cases, is, well, it includes all non-interactive search assumptions or like decisional assumptions. And let me say what I mean by, maybe I'll say a word. So decisional assumption just says the assumption is you cannot distinguish between two probabilities. That's a decisional assumption. So we have various of those, obviously, that we know of. And a search assumption is any assumption that, like a RSA or factoring, that you're given a query, you come up with an answer, but you can check if your answer is correct. Okay, so any kind of search assumption or decisional assumption, you won't be able to prove security. And like I say, you can probably extend it to other assumptions, but it's case by case. You won't be able to extend it too much because the assumption that the scheme itself is secure kind of is a block there. Okay, I won't have time to say much about the proof. I'll just kind of highlight the very, very vague idea. So the vague idea is the following. And like I said, this part is the technical part. So what the idea, and here is, I think, the nice idea to take home from here is the following idea. Well, I want to say that the reduction or the adversary that breaks the assumption, I'm just using the encryption as the assumption for simplicity, that he doesn't need the prover. The prover will not help him. Why? Why does he not need the prover? Well, look, he gives the prover queries, he gets answers. There are two cases. He gets to answer, AI. Either he can decrypt AI. Either AI he gets an encryption of AI. Either AI is, he can't decrypt it, so it's useless. So definitely you don't need him. Or he can't decrypt it, and then what we prove, if he can decrypt it, actually we can use him to decrypt QI, the query. So that's kind of the main idea. Let me make it maybe a bit more precise. So here's how we prove. Well, we first check if that reduction or the A is sensitive to the query. What do I mean by sensitive? Well, I mean, I'm going to give A, for each answer AI, I'm going to feed him all the possible answers for AI. See if he behaves differently. See if he's, if it changes his behavior. Well, there's some assumption here, I won't go into it now, because I don't have time. Well, and then we look at the sensitive set. And this is the main point. What we prove is that if he's sensitive to AI, namely, he behaves differently depending on what you encrypt inside there, then we can use him to find QI. And once we have so the thing that he's not sensitive to, definitely we don't need the P star, just feed him garbage. He's not sensitive. For the ones that he is sensitive, we use the no signaling prover to compute the answers. And the fact that there exists a no signaling prover means that we can simulate this prover with a correct distribution. And again, that's something that Mark Fishkin talked about in his talk, which is kind of easy to get these negative results wrong for this reason. But I won't get into it. Okay, so this is the summary of the result. We showed a very strong connection. We showed between delegation and no signaling provers. Essentially, we showed that if the MIP is statistically no signaling, then the one-round argument is secure, and it's in some sense an if and only if. The main open problem, can you do all of X? Or the scaled down version of P. If you can, we have a two-message delegation for P, and I think I'm going to retire if that happens. So, yes?
So, if you use the fact that MIP with this no signaling contains P space,
yes,
and you get a delegation protocol with log space, but that's not particularly
well, we knew that already. That's the thing.
Well, how? By GKR?
Yes.
Okay, good. But GKR does a little bit more. right? I mean, it does
NC.
So, well, but GKR is a different protocol.
Okay,
than
so let
this.
me, okay, so, yes, I'll tell you, GKR, you can think of it, I need to explain more, but I'll just say in a word, you can think of it as a no signaling and MIP. If you open it and think of it as no signaling, as an MIP, it turns out there's no signaling. That's why you can.
So then you show no signaling MIP for something bigger than P space, right?
No, the scaled up it's like
No, I know you're right. No, but actually, you know this right in some sense. No, because and NC, it's
What is
the
NC?
scaling
What's
up
the
of
scaled up
NC
version?
is P space in this case.
but it's a little different. Yeah, it's
Is it?
GKR doesn't give you an interactive proof for making P space.
it doesn't give you for more than P space, but it gives you for something different. Let's take that offline. Thank you.
Scaled up version of NC.
See, how does it relate, or I guess maybe there were already previous conjectures by Boaz, Yuda, and Salil, essentially about the soundness, or our paper with Salil about condensers. How does it relate to Fiat-Shamir heuristics? So, for example, if you take a 4-round protocol and assume that a condenser exists, that will be enough to get you a 2-round protocol, but the assumption is not falsifiable? Or?
So wait, you're asking if you have a 4-round like argument and use the Peel scheme, whether you'll get something that's secure?
For argument, it's actually false. So for argument, yeah, I was going to say for proof. So we don't have a proof, right?
Okay, if you start with a proof, it's secure. That's the result I have with Ran. If you start with an actual proof and you use the Peel scheme, you'll get something secure. If you start with an argument, there are negative results that show it won't be
But
secure.
we don't know any proofs. We don't know any constant round proofs. We only know constant round arguments, right?
Yes, we don't know any constant round proofs for something that's more than Arthur,
Another thing, so they do, you may have said it and I lost it, but so they've shown in the quantum world that there's a difference between, that this no signaling guys
Yes.
are different than interactive proofs.
No, they didn't.
No, interactive proofs mean,
They show that it contains P space, and it's contained in exp. But they don't know where it is. It may be P space.
So for
It may
two
be X.
provers, they showed that it is P space, right?
For two provers, it's P space.
Right. But somehow
you
in the
don't care about
quantum
the number
world,
of
2 and
proofs.
3 are
Are different. And may be different.
You don't care about the number of provers, right?
We don't. I'm just saying, right.
Yeah, I mean,
No, I'm just saying,
in
if
the
you try.
in the
No, I
physical
mean-
world, two and many are the same, but in the quantum world, at least in the auto Merling, it's not the same.
No, but it does give you an indication. If you don't start with a two-prover inductive proof and try to get an argument, because that you won't get more than P space, and the P space we know. Or log
I
space.
think that
going down.
like in the classical, you would have intuition that if 2 provers are P space, everything is.
Any more questions?
Thank you.
Thank you.